In this presentation, we're going to talk about stacks and the role they play in the programming concept of subroutines. Shown here is a very simple architecture, and the program that we are going to try and run is going to be held in memory. And the job of the program counter, shown here in green, is to tell us where the next instruction is. So we imagine we're somewhere in the middle of executing our program and we want to know what the next instruction is. That is the job of the program counter. But not only do we have instructions in memory, but we also have data. So the instruction might tell us to go to a particular memory location and get its value. That's what we mean by a variable, after all. So the program counter cannot be directly connected to the memory because we need things other than the next instruction. Sometimes we need data. But this is the role of the program counter. We see that in this architecture, the program counter is connected to the bus by a two-headed arrow. And this means that it can put its information onto the bus, say to be given to the memory address register so we can access the next instruction. But it can also get information off the bus from some other device. And so that means that the program counter can do a job other than just count to move to the next instruction, but it can be changed to an entirely different number. Next, let's imagine a jump or goto instruction. Let's imagine it was at location 12. So the program counter was pointing to 12, and we go to 12 and we get this jump instruction. And part of the fetch cycle moved the program counter from 12 to 13. That's our normal progression through a program, is linear. You move from 12 to 13. So the program counter was given the 13, assuming that the next instruction in the program, it will be 13. But this jump instruction is going to change that. It's going to give some value to the program counter and move to another part of the code entirely. A slightly more complicated instruction is known as a conditional jump. So we will change the PC, the program counter, which is a jump, or leave it unchanged based on some condition. So we will do some kind of comparison. That comparison will end up in our the flag part of our architecture, and then based on the flag's value, we will either put the new value in the program counter and perform the jump or not. So it's a jump based on some condition, jumping or not jumping. And this is how, at its lowest level, how we get the high level concept of ifs and loops. They are conditional jumps at this lowest level. Next, let us consider a subroutine. So you have some code and then it calls a subroutine. So we are going to jump to the part of memory holding the code that is the subroutine. And so we are calling the subroutine or passing control to the subroutine. But the difference between this and a regular old jump is that we want to return. We want to go back to what called us when we are done executing the subroutine code. One reason for subroutines is to reduce repeated code. So there might be some action that we might want to perform in a number of different times from a number of different locations within our program. So we need to return to whomever called us, and it's not necessarily always the same place. Therefore, we have to somehow remember the return address because it's not always the same. Now let's imagine we're executing some code. It's in memory. We are going to line 12, and it says for us to call a subroutine. So in the fetching of that instruction, we had changed the program counter from 12 to 13, but now it's going to have us move to some entirely different location. But at some point, we're going to want to return, and we want to return not to the call, but to the instruction after the call, the 13. And so it is the program counter which holds the 13 that's what we need to remember before we go changing the program counter to, I don't know, the 47 or wherever the subroutine is. So we need to store the program counter. Remember that 13 so that we can get back there. If you were going to limit yourself to going to one subroutine, executing whatever code, and then returning, then you could get away with having sort of a special purpose register for the purpose of holding the program counter, holding the return address, or you could have a special, location in memory for that job. But we want to allow a subroutine to call another subroutine, to call another subroutine. And so to have just one location in memory or one register is not satisfactory. So let's look at a simple scenario of a program calling a subroutine and that subroutine calling another subroutine. So let's say that we started in a part of the program that we're going to call main, and then it's going to call subroutine A, routine A. So at some point we will want to get back to the main program, so we need to store the main return address, which was in the program counter. Then we start executing some of the lines of routine A, and we find that it calls routine B. So at some point we're going to want to get back to routine A, so we must store routine A's return address. Now we're in routine B, and we're executing the code in routine B, and it finishes and it wants to return the control, get back to routine A. And so we need the address that we stored that was called routine A's return address. So now we're back in routine A. We execute whatever code remains in routine A, and then we finish that routine, and we're ready to return the control to main, and we need the main's return address. And so if we look at what's going on with these return addresses, we see that the first address that we need is the last address that we stored. When we're in routine B, we need to return to A, and that was the last address stored. And then when we're in A, we need to return to main, and that was the last address stored because we got rid of returning A. When we returned to A, we got rid of that. And so this is the rules of a stack. This is the LIFO protocol. So we see that a subroutine call is like a push, and a subroutine return is like a pop. So the subroutine call actually requires pushing the value of the program counter, the return address, onto a stack. And then it can change the value of the program counter. The return from a subroutine involves popping that return address from the stack and then placing it in the program counter. That's how we return. And I'm just showing here some of the references used to put together this presentation.